Here is a tutorial dedicated to reverse engineering. We will see here the study of a liquid mixer. For this liquid mixer, we will start with a model project of propelling propellers in water. We will determine the basic parameters of the project. Here we have a mixer for oil. We will modify the ambient fluid and choose oil. The objective is a propulsion propeller, and the operating point with a fluid velocity in the tank which has 0. But we need to enter a non-zero speed, so we'll enter 0.01 seconds. And a rotational speed of 50 rpm. So much for the operating point. So 50 revolutions per minute and 0 travel speed upstream. For the geometry of the blade, we will use here the indications of a customer who has an existing propeller, whose drawing is hidden for requested confidentiality. We measure the dimensions on the existing propeller to define the blade tip radius and the blade root radius. Here we use a drawing of our blade, giving the angles and dimensions to the various radii. We obtain the radius at the tip of the blade, and the radius at the root of the blade. We therefore use the existing propeller to obtain the geometric dimensions. We will also note on the existing propeller the chord at the foot of the blade and the chord at the tip of the blade. So what is the chord at the foot of the blade and the chord at the tip of the blade? The chord at the blade root is the width of the blade at the hub, and the chord at the blade tip is the width at the blade tip. The width at the root of the blade obtained is 79 millimeters. And the chord at the tip of the blade is 250 millimeters. We will then click on Linearize to create a linear distribution between the chords. We have defined the chord in blade feet and the chord in blade tip. So, to summarize, we used the geometry of an existing propeller, according to an existing drawing. The drawing is hidden for confidentiality, but any propeller drawing is usable, with a division into 5 elements, delimited by 6 profiles. So we have the basic geometry of our propeller. For the moment we are not worried about the calibration of the profiles. So we just entered the basic geometry of our propeller. We just have to define the number of blades. The loaded model had 5 blades. We will reduce this number of blades to 3 blades, and return to the Geometry tab. So to change the number of blades, we used the Optimize tab and changed the number of blades. We are going to do a first test of our propeller, using the normal design method. That is to say that the software will apply the optimum instances for this propeller, with this geometry, and a classic aerodynamic profile. Performance and twist will be calculated according to the operating point. So to build the propeller whose geometry we have determined here, we just have to click now on Build the blade with the optimum. So the calculation of optimum twist and performance is done. The 3D model is updated. And we see our propeller. In the lower zone of the interface, we have the results. The axial force on the propeller, and torque at the propeller shaft. We also have the pressure delta upstream and downstream of the propeller. There is one thing that will interest us for our mixer study. It is the speeds produced at the propeller outlet. For this, we show the fluid speed results. And here we see a table of speeds downstream of the propeller. The velocities at each element are given here. Here it is the downstream speeds, tangential, representing the rotation of the fluid downstream of the propeller. And that is the axial downstream speed, therefore the acceleration of the fluid, in the direction of the axis of the propeller. Using the Show button and Show Particle Path, we see the induced velocity vectors at the element level. Starting from 0 speed upstream, we have an acceleration, but also a rotational movement, which is very weak. So here, our propeller mainly generates an axial acceleration of the fluid. We could export the 3D geometry of these blades with the optimum twist using the File menu, Export in IGS format, and open them in a CAD type SolidWorks. So we have created here a propeller with optimum twist and settings. We can apply different settings by using the menu, Management of Attack Angles. Here, for example, we are going to modify the angle of attack at the level of the third element. We are going to select a much stronger angle of attack. We are going to change to 20 degrees. And we apply this incidence of 20 degrees to all the elements. So force all the profiles to the incidence of 20 degrees. Our propeller has been rebuilt. The incidences of the blades have been adjusted to 20 degrees. An important nuance of vocabulary must be clarified. The pitch is the angle formed by the chord of the profile with the plane of rotation. The incidence is the angle of attack actually perceived, taking into account the induced velocities. The propeller will modify the relative direction of the fluid. It will accelerate and put in rotation the fluid upstream. The propeller will therefore cross a fluid modified in terms of speed and angle. So the angle of incidence does not correspond to the pitch angle. There is a difference. So here, in this new propeller, with forced incidences at 20 degrees, we have axial speeds and tangential speeds, which have been greatly increased. we show these tangential and axial speeds. And a rotation. We're going to slow down a bit. If we look in front plane, here, we see that the particles have a tangential deviation, much more important than previously. So our mixing is also done in a tangential way, in this configuration there. The particle which was here, describes a trajectory of crossing the helix, which moves it like that. So these tangential velocities are given here for each element, and the axial velocities are given here for each element. So this is how a mixer is created, with angles of incidence generating greater tangential mixing. Here, we have incidences and wedgings which result from a twist, respecting the displacement of the fluid and the rotation of the fluid. The phenomena produced by a sheet metal propeller, bent without respecting the flux angles crossing the propeller at the operating point. Are complex and hazardous phenomena. This is why it is advisable to use the Heliceal software before the design, rather than after the design. But the Heliceal software offers, despite this, the possibility of evaluating the performance of an already existing propeller in reverse engineering. To do this, we are going to switch to reverse engineering mode. In the Geometry, Reverse Engineering tab, we activate the Reverse Engineering option. This has the effect of proposing a setting table, which will define the geometry of an existing propeller. So here, we are going to enter the profile calibration table, and no longer let the software calculate the best calibrations. We have measured our settings at various radii, and we are going to enter these values into the software. So the footer calibration is 36.5. So here, we will enter 36.5. The profile 2 setting is 38.6. We enter 38.6. The setting. At profile 3, 41.85, we enter 42, then 31.5. Then 39.5, then 31. Reverse engineering does not allow entering a different last setting. For technical reasons, it is important that the last two profiles are at the same setting. So we have a slight delta between 24 and 31 here compared to reality. We are now going to test the performance of this propeller with these imposed settings. Here is our rebuilt propeller, with its reverse engineering table. In advanced options, geometry and generator shape, we could bring the generator axis closer to the leading edge so that the 3D model looks more like the real geometry. And in the geometry, at the level of the blade dimensions, we can modify the distribution of the chord lengths so that they correspond better. So we have here, at the level of profile 4, a chord which must be around 340 millimeters. We are going to modify the curve of the distributions to increase the chords so that they reach 340 mm at the level of profile 4. So the control chords is not unitary, but global to maintain a regular and coherent geometry. So we're going to shape the shape here, up to 340 mm. At profile 4. We thus obtain a distribution closer to the existing propeller. So we will now test the performance and rebuild the propeller in reverse engineering. Here is the propeller built with tables. We can now test different rotation speeds and analyze the results. Fluid speeds, power consumed, pressure delta, etc. But remember that the approach of starting on an existing propeller is a more complex and risky process. We are going to go a little further in the definition of our propeller. The profile of our existing propeller in sheet metal is flatter than the profile of our 3D model. We will therefore see how to modify the profile to obtain a profile that corresponds more to reality. To do this, we go to the profile data vars of the Heliceal software. Select a profile with a smaller thickness. Here, the NACA 8503 profile. And apply this profile. In the reverse engineering table, we apply the profile to the foot. And it should be applied for each element profile. So voila, we applied the profile to each element. So we have a mixer propeller, which matches the existing propeller better. Here we see a rupture alert on element 1, which says that the forces generated will create a rupture at this level. In the geometry we can define the material. In the Geometry tab, Geometry Advanced Options, Element Reinforcement, we click on Choose Material to determine our material. And choose Steel Stainless. We click on Use the material of this reinforcement for all the elements. Here, despite the definition of material stainless steel, we still have a break. We can see in the resistances that here the bending moment is slightly higher maximum allowable. We will definitely have to choose a thicker profile for this element. In the hypotheses, we have set a safety factor of 3. And even with a safety factor of 2 we still have a break, so we will have to choose a thicker profile for the blade root. So that's it, as far as retro designing.